Welcome to Circuit Analysis 1, and we're continuing our study of AC circuits. And we know that AC reacts to capacitors and inductors in a circuit, and we know that the voltage and current will develop a phase shift between them. Capacitors and inductors are frequency-dependent components. However, if it's a purely resistive circuit with an AC source, voltage and current do not develop this phase shift, but they're in phase with each other. So we're in chapter 20. Any changing current in an inductor will be impeded. The current will be impeded as a result of the inductance associated with it. Inductive reactance in ohms is proportional to frequency. And I gave a couple examples right here of an inductor in a circuit with a change in frequency, and we should know how to calculate inductive reactance. And we should I did a couple different frequencies here, and we should realize that at high frequency, an inductor will block the current. At low frequency, there is low resistance to current flow in an AC circuit. Capacitive inductance is inversely proportional to frequency. And here's an example of X sub C. And to understand what happens at different frequencies, we did a calculation of different frequencies, and we can see from these calculations that at high frequency, capacitor has very low resistance. But at low frequencies, X sub C has a high resistance, so we use that to block DC signals. Here's an AC circuit with a purely resistive load, and we should know how to convert between voltage or current peak and voltage or current RMS. There's no phase shift between voltage and current in a purely resistive circuit, as we can see here. We have an RMS voltage at 20 degrees and our current RMS is at 20 degrees. No phase shift if it's purely resistive. If it's purely capacitive, we will have the current will lead the voltage by 90 degrees, and we can see that by our result here. So I have the voltage divided by current and end up with 110 degrees, 1.77 amps current RMS. The voltage RMS is 7 at 20 degrees. So the current leads the voltage here. And by 90 degrees if it's purely capacitive. In a purely inductive circuit, the current will lag by 90 degrees, and here's an example with a 200 millihenry inductor, and we have the angular velocity, so from that we can compute X sub L, and we get 1.26 K resistance, and we divide the magnitude, subtract the angles. 20 minus 90 gives us 5.6 milliamps at minus 70, where the current lags the voltage. Now here is where it gets a little more complex. We have not a purely inductive circuit or resistive, but it's an RL circuit. So make sure you understand real complex numbers in mathematics. In electrical engineering, we'll be using that a lot. Shown here also is the impedance triangle. And since this is inductive reactance, it's at X sub L is positive 90 degrees. If we're given a voltage source of 100 volts at the origin of 0, and by the way, if no origin is given, if there's no phase shift given, we're always assuming it starts at 0. We have a load here of R equals 120 and X sub L equals 75. And we want to compute the peak current. So the first thing we want to do is we want to find the hypotenuse Z of the impedance triangle. And we're going to use Pythagorean's theorem, and we get 141.5 ohms. Now determine the angle of this vector. So we have x over r, and we get the inverse tangent of that, and we end up with 72 degrees. So current equals voltage divided by Z, and here it is right here. We have 100 divided by 141.5. 0 minus 32 gives us a minus 32 degrees. So here the current lags the voltage in the RL circuit. And it's only by 32 degrees in this example. Notice that in the capacitive reactance, we have a resistor and a capacitor, but we're expecting here an X sub C, which is going to be at minus 90 within the impedance triangle. We can use trigonometry to solve many of our problems. So we want to find the peak current. We're giving a voltage of 16 at 0. We're given these values for R and X sub C. First thing we want to do is determine the Z side of the vector, and then we're going to divide the peak voltage vector by the Z vector. So here we are, we end up with 731.1 for Z at minus 40 because it's X sub C, and we get 0 minus negative 40, we get 40 degrees. So the current leads the voltage in an RC circuit. Here are a couple problems, homework problems for you to get some experience with these type of examples. Now, we have three components here. We have a resistor, an inductor, and a capacitor. How do you determine the total impedance of this circuit? First, as rectangular coordinates, we write out each in ohms because we can add and subtract in rectangular coordinates, and we divide and multiply only in polar coordinates. So we need to be able to go between polar and rectangular systems. Rectangular coordinates here would be R is 30, that's a real number, but X sub L is an imaginary number, and we have to use X sub L, and it'll be positive J, and X sub C would be a minus J imaginary number. We use J in electrical engineering because I is used for current. We're going to combine the like values, so we end up with 30 minus J plus J, and 88.646 negative plus 7, so we get 30 minus J 80.94, so we combine those like terms. And now we use the Pythagorean's theorem again, and we get 86.3 for our Z side, and our angle is at minus 70 degrees. Now we can determine the current. Since the voltage was given in RMS, we don't have to convert from peak to RMS. So we end up here with voltage RMS divided by Z, 120 divided by 86, 0 minus negative 70, and we get 1.470 degrees at amperes. So try your hand at this for homework as well. There is a direct relationship between the impedance triangle and the power triangle. Here's the impedance triangle, here's the power triangle. One thing I noticed that this is a lot bigger, however the angles are the same. And the power triangle is comprised of real power to do work, and that's P in watts. And it's derived by multiplying the current squared by R. So we find current, we do I squared R to get P. Q is the reactive power. I squared X will give us Q. It can be positive or negative. And that's in volt amperes reactive. And S is apparent power, and we calculate that by I squared Z, and that's in volt amperes. The angles are the same. Again, we use the tools of trigonometry to solve a lot of our problems. Let's look at the circuit here. We have a 75 ohm and a 100 millihenry inductor. We want to derive the impedance and power triangles for this circuit. So the first thing we want to do is compute the inductive reactance, since we have an inductor here. And we're only given 60 hertz here as any information to use. So we use 2 pi f times L. Don't forget X sub L is directly proportional to frequency. We get 37.7 ohms. Z, now we can solve for Z. We have 75, 37, and we use Pythagorean's theorem. We get 84, and we compute the angle as well, the arctangent of X over R, and that gives us the value of 26.7 degrees. So voila, we have the impedance triangle right here. So now we want to move over to the power triangle. So we want to determine current first, and that's just the voltage divided by Z. So we're given voltage of 440 volts, divide that by 84, and we get 5.24 amperes. Next, we're going to multiply this current square times each side of the impedance triangle to get the power triangle. So we do I squared R, we get 2.1 kilowatts, and that's our power to do real work. We have Q, it's our reactive power, I squared X, and we get 1K vars. And then we did S is computed I squared Z, and we get 2.3 kVA. And while we're at it, we're going to compute the cosine of the angle, which is the power factor. It has an effect on power. We'll talk about more of that later, but again, we're using a lot of trigonometry to determine the cosine of the angle, which is 27, or we could say it's P over S. It's the adjacent over hypotenuse. We can do the same with the impedance triangle, but we will get some differences, especially when we have something really big numbers like this. So we have to be careful. We want to use something that's more accurate if we can. Here's the results of our calculation. We have the impedance triangle and the power triangle. The same angle and just a bigger triangle here for the power triangle. So I want you to try your hand at these types of problems, and that's it for now. Have a good day.